Okay, so we have Matthew Sutcliffe and Richie Yeung, who will be talking about machine learning and classical simulation with ZX diagrams.
Yeah.
Okay.
Hi everyone. Yeah, today Matthew and I are gonna give an overview of circuit simulation using ZX and how machine learning is applied to ZX. I'm gonna start by motivating why we should use machine learning for ZX, give some background, and then some brief overview of how um, machine learning has been applied to ZX so far. Matthew's gonna talk about um, simulation in ZX and some work we've done with Alice Cozier recently on combining reinforcement learning with ZX to speed up quantum simulation. So yeah, why would we want to apply machine learning to ZX? Like ZX is already great, right? Instead of working with vectors and matrices, with the ZX calculus, we can represent and reason with quantum computation as graphs. As humans and ZX practitioners, we think this is simpler and more intuitive. But what about from a computational standpoint? From a computational standpoint, ZX calculus combines a lot of existing quantum compilation techniques and algebraic structures, such as graph states, summable powers, power exponentials, stabilizers, so on, into a single unified framework. This allows us to interleave these techniques by applying rewrite rules, like interleavingly without changing notation. Next slide. But how do we decide what the good rewrites are? Like which rewrites do we apply with so many of them? A graph with n vertices can have up to like n squared edges and around 2 to the n subgraphs. So the search space of which rules to apply can be very large. We also need to somehow apply these rewrites to lead to good optimizations like further down the line rather than just applying them greedily against our objective. So we need some way to do some look ahead. There's also the question of how to, not yet.
Sorry.
That's okay. There's also the question of how to apply these rewrite rules in ensemble for different families of diagrams and circuits. With traditional algorithm design, we would have to come up with different strategies to take advantage of each of these different circuit classes. We have to tweak the algorithm somehow to make the most of these different types of circuit classes. Next slide. Or we can get machine learning to work out the algorithm for us. In very basic terms, we can use neural networks that consist of layers of linear and nonlinear calculations to approximate arbitrary functions. And then we use gradient-based optimization to fit the neural network to a data set. So yeah, using say gradient descent, we can fit this neural network to any arbitrary function. So in theory, we can fit a function that takes in a ZX diagram digitized into some sort of tensor as input and output an optimized ZX diagram as a tensor as output. Or it can also output something that represents the rewrite to be performed on the ZX diagram. So as you can see, this technique is very general and it's not is you can apply this to a wide class of circuits and a wide class of different problems. Next slide. We don't have time to go into different like details on every single type of neural network, but I'll give a very light overview. So we have convolution neural networks, which are good for images, and they work by updating the vectors or the embeddings based on its neighbors, its local information. It's a local update. And then you also have recurrent neural networks and transformers, which are good for sequence data, natural language processing, or like just arbitrary sequences by combining the vectors or embeddings of tokens or individual words into a single sequence embedding. And in particular, the transformer uses a attention mechanism also to take sequences of vectors and combine it to a single vector. We also have graph neural networks, which is good for processing graph data, which will end up coming up a lot in this topic because ZX diagrams are graphs, right? And also there are convolutional and intentional variants of graph neural networks that use similar techniques as convolutional neural networks and transformers. So yeah, we're going to focus more on graph neural networks with ZX diagrams. Next slide. In particular, reinforcement learning is a useful technique because particularly for rewriting ZX diagrams because with reinforcement learning you can apply actions in such a way that you stay within the semantically correct set of ZX diagrams, right? So the way reinforcement learning works is you have an agent that acts in an environment, and the environment will be interacting with some sort of ZX diagram, and it would act according to a policy. So there's some sort of policy in which it performs these actions, and each step, the agent receives an observation, which is a ZX diagram typically, and it responds with an action, which is typically a rewrite rule, and it results in a reward, some sort of, which is reflective how much optimization is done. And the aim is to maximize the amount of reward. So the agent will play out this game. It's called a rollout. And after the rollout, it collects data about what kind of reward it gets after each action. And then it will try its best to work out a good strategy based on that. Next slide. So I'm going to highlight 3 pieces of work that uses machine learning on ZX diagrams. We have this first paper that by Negale and Macard on optimizing ZX diagrams with deep reinforcement learning, and we also also using reinforcement learning to do quantum circuit optimization. And then there's some work that I've done with Konstantinos, Alexander Krajnobrink, and Francois Charton on rewriting ZX diagrams using transformers. Yeah, next slide. So for those first 2 pieces of work, they both use reinforcement learning. And with RealL, the aim is to reduce the number of 2 cubic gates in a graph-based ZX diagram. And in the other piece of work, they're just trying to reduce the number of spiders of the ZX diagram. And both of these kind of paved the way to large-scale ZX rewriting using machine learning. And the work that I worked on using transformers doesn't use reinforcement learning, but rather it takes in ZX diagrams tokenized into sequences of characters, and transformer treats these sequences directly as a sequence task, and it parses those sequences back into a ZX diagram. So it's entirely possible that the output ZX diagram is not semantically correct. So it's kind of a proof of concept as well. So yeah, that's it from me, and I'll pass it on to Matthew.
Yeah, so thank you, Richie. So we've seen how reinforcement learning can be applied to optimization in particular with ZX calculus. Now we're going to move on to more recent work, which is kind of still in development with myself and Richie and Alex Koziel-Pipe, where we're applying reinforcement learning for classical simulation with ZX calculus. So very, very briefly, as I'm sure everyone in this call will know, if you have some ZX diagram that's scalar, so no open inputs and outputs, if you apply the rewrite rules and the graph is Clifford, it'll just fully reduce to some scalar number, which will correspond to its probability amplitude. Whereas if you have the Clifford T-gate set, then you'll end up with something like this, where you have a bunch of interconnected T-gates and maybe some zero phase in there. So at this point, you'll need to rely on some decompositions. So for instance, this is the current state of the art asymptotic decomposition, which essentially allows you to exchange any set of 4 T spiders for a sum of 3 stabilizer terms. So we say this has an alpha efficiency of 0.396 because the number of terms you get out scales as 2 to the alpha T, given a T count of T. In practice, however, every time we apply some decomposition and it branches the total number of terms that we have to deal with, at each step we apply more of the simplification via the rewriting rules. So in practice, we actually have an effective alpha, which is usually much smaller than the actual decomposition alpha. So in this case, the effective alpha, if you just apply this decomposition over and over for your average graph, will be something closer to 0.3. And there's a few ways to improve efficiency. There's really 2 main ways. One is to find new decompositions that have a lower alpha. So as I say, this is the state of the art. Before this, there were decompositions with higher alphas before this one was discovered. I'm sure new ones will be found at some point. And then the other way really is to take the decompositions we already have and to find smarter ways of determining where we should apply it rather than just kind of applying it indiscriminately. And then there's a third category for just kind of other. So for instance, Alex and I managed to show that some of this work can be parallelized on the GPU. So that doesn't really fit into either of these categories, but it does give a big linear speedup. So to look at the two main methods for improving efficiency. So the first I said is finding new decompositions. And this can involve decompositions which are not kind of universally applicable. So for instance, these are the cat states, well, two of the cat states. So this top one, for instance, I think has an alpha efficiency of 0.25, so much better than the magic 5 decomposition I showed a few slides ago. But this is only applicable in very specific cases, right? So you have to have 4 T-spiders that are all connected to one 0 or pi phase spider. So you can only apply this in certain places. And then the next method is to find smarter ways of deciding where to apply the existing heuristics. So where to apply the existing decompositions using heuristics. So for instance, the top here, I'm showing a very simple decomposition. And if you were to apply this cutting decomposition to a T-spider, it would have an alpha efficiency of 1, which is generally really bad. So usually this is kind of avoided. But if you apply it in specific cases and you kind of analyze where you want to apply it, then it can be very effective. So in this particular graph example, if you were to cut this spider, which I've crossed out with a little X, you'll see that these two gadgets will now have the same neighbor set, and so they will be able to fuse together with gadget fusion. So these two orange labeled T-spiders would fuse together. And similarly, this one here would only have two edges on this 0 phase spider, meaning that essentially it would just collapse, and this little green spider would fuse with this one, and likewise this purple one would fuse with that one. So in effect, we'd have removed all 7 T-spiders with just one cut, so just 2 turns. So that would have an effective alpha of 0.14, so 1 over 7. But how do we decide when and where we should be applying these? Well, that's quite a hard problem, and there's lots of heuristics that try and find generally applicable cases where it might be useful. But you're often going to miss kind of little tricks here and there. So this is where reinforcement can come in. So as Richie showed earlier, reinforcement's been used for optimization, where the action space is just the rewriting rules essentially. And you use this to simplify your graph, and it gets rewarded when say for instance, the T count is reduced. Whereas in this case, what we'd be doing, the action space would be the decompositions. So it can choose which decomposition to apply and on which set of spiders. And whenever it applies decompositions that, after a few iterations manage to have a lower effective alpha, so it removes more T-gates at the cost of fewer turns, then this is more highly rewarded. And then just to kind of wrap it up, there's some preliminary results. So this work is still very much ongoing, but we do have some early results where we've managed to train a reinforcement learning model on the Magic 5 decompositions. That was the first one I showed. So currently, the state of the art uses the cat decompositions wherever possible. And then when there are no more cat states left, it will rely on this Magic 5 decomposition, and it will pick the 5 T-spiders onto one which to apply it randomly. Whereas what we do here instead is, rather than picking those 5 T-spiders randomly, we use the reinforcement learning model, which is trained to decide which spider should it be selecting for this decomposition. So these left 2 bars show if we do this 5 only, we managed to reduce the effective alpha by 0.1 just by using this model rather than randomly. And then if we bring cats into the mix, then it's a much smaller decrease in alpha, so it's about 0.01. But if the T count is large enough, then this still corresponds to quite a large difference in the number of turns and hence the runtime. So we think there's a lot of potential here if we bring in all the other decompositions as well and let the model decide which decomposition should I use at each step and on which T-spider should I apply it. So this is the future ongoing work here. And if you have any questions, Richie and I will be happy to take them.
All right. Thank you very much, Matthew and Richie. We have time for a short question.